So students, so today I would like to give the expression, I would like to derive the expression for field intensity due to dipole on its axial line. Since the field view is very less, I'm just moving my page here. So for that, initially I have taken a dipole of length 2L, and I am considering the positive charge on my left and the negative charge resides on my right side. Maybe in some books or in some material, the negative charge is considered here and the positive charge is considered here. So as we say the axial line, which means the axis which is passing through the length of the dipole, that line is known as the axial line. So here I am taking a point P where I would like to calculate the field intensity due to this dipole. Right? So due to the negative charge, we know that the field direction is towards the negative charge. This is why I am recurring this one. And due to the positive charge, the field intensity is radially outwards. And assume that the point P is at a distance of small r from the center of the dipole. Here this is the center. So as we discussed in the classroom, the length of the dipole is considered as 2L. Right? So this is the simplest case we are assuming here. So for this we are applying that superposition principle. So first of all, we would like to calculate the field intensity due to the negative charge, which is at a distance of r minus L from the point P. Since the total distance from here to here it is r and the center to the negative charge is L, the distance between negative charge to point P is obviously r minus L. So first we have to write the expression for the field intensity due to the negative charge, that is represented as E minus, given by 1 by 4 pi epsilon naught, and here I am taking the charge is the Q by the distance of separation between them is r minus L square. So this is the most generalized expression for the charge field intensity due to an isolated charge, that is kq by r minus L whole square. Likewise, due to the positive charge, the field intensity at point P. So that can be written as E plus is equals to kq by r plus L square, isn't it? So here I would like to take that field intensity E net bar is given by E1 E plus bar plus E minus bar. This is the vector notation of the field intensity. So here I would like to calculate the magnitude of the field intensity first. So according to the law of parallelogram of vector addition, so here at point P, both E minus and E plus are acting opposite to each other. So here the angle between them is theta 180. So if I am writing the expression for modulus of E net bar, the end result may be something like E minus minus of E plus. So this is very simple mathematics we can do in a separate way, right? So this was discussed even in the classroom itself. So I am simply substituting the values, respective values here, that is kq by r minus L whole square minus kq by r plus L whole square. So here there is a doubt, why I am taking that E minus of minus E plus? Why can't be this is E plus of minus E minus? Why I am taking the E minus first and the E plus later? So this is very simple to convey that as intensity is inversely proportional to the square of the distance between them. Whenever the R value increases, the effective value of the R increases, intensity decreases. So whenever the R value increases, E decreases, and R decreases, E increases, isn't it? So that is why, so here the negative charge is very nearer to this one. So R is very less and E is obviously more. And R is more, E is less, isn't it? So that's why I'm taking the E minus first and then E plus later. So by simply calculating the expression for this, I'm taking KQ as common. 1 by r minus L whole square, minus 1 by r plus L whole square, and this is kq r plus L whole square minus r minus L whole square by r square minus L square whole square. This implies kq. You can do it on your own, and the end result is 4rl by r square minus L square whole square, and this can be written as 1 by 4 pi epsilon naught. K is 1 by 4 pi epsilon naught, and kq into 2l into r into 2, I can say, by r square minus L square whole square. So here 2L into Q, this is nothing but the length of the dipole into charge. That can be written as the dipole moment. I think you can remember the dipole moment concept. So by eliminating this, by replacing this 2L into Q, I can write the P, and the end result may be written as K into 2PR by r square minus L square whole square. This is equals to E value. This is the magnitude of the E, right? So this is the end result for the field intensity due to the dipole on its axial line. So this can be written as E axial, I can say, right? So for a short dipole, I am taking a special case here. For a short dipole, that is r much greater than L, then L square can be neglected, which means E axial expression can be turns as, since L square can be neglected, r square power square, that is r power 4, r power 4 lo r cube times potundi. So I can say 2p by r cube. This is the a special case of the field intensity due to the dipole on the axial line due to a short dipole. So please keep this equation in mind. This is most useful for the numerical problems. Got it? Right.